Hello student and welcome to the first lecture of chapter 2 names, scopes and bindings. So in this chapter we will learn what are the names and the scope of that and the bindings between them. So let us start with the first point, that is the name. So a name is exactly what you think it is. So basically names are the identifiers. So we can use the different symbols for the names also. For example, plus symbol also. So name identify what we used. Okay, for example, identifier. Now binding. So binding is nothing but an association between two things such as a name and the thing it names. Okay, so association between the name and what it contains. Now the scope of a binding is the part of the program in which the binding is active. That association of where that is active is called as the scope. The binding time is the point at which a binding is created, or more generally the point at which any implementation decision is made. That means the association made between the name and what it contains, the time. That time is called as the binding time. So the binding time will be the language design time. So here programmer structure or programmer will decide the program structure, different types which will be used with that language. So that will be bind at the language design time. Now there is a language implementation time also. So here IO operations, then arithmetic overflow, then type equality. So that all will be decided at the language implementation time. There are some implementation decisions also, like program writing time. So algorithms, then names, then there is a compile time binding also. So this will be done at the compile time. So that indicates the plan for data layout. Then there is a link time binding also. So this will be basically done by the linker, and it contains the layout of a whole program in a memory. There is a load time binding also. So load time binding, so basically it is done by the loader and it decides the physical address of the program. Now next is the runtime binding. So here values and variables bindings will be done at the runtime, and the sizes of the strings, this will be also decided at the runtime. Then there are different subsums also, like program startup time, then module entry time, then elaboration time, then procedure entry time, block entry time, and statement execution time. So all this will be decided at the runtime. Now next important terms are static and dynamic. Okay, so there are two type of bindings, static binding and dynamic binding. So they are generally used to refer to things bound before runtime and at runtime respectively. Okay, so the binding which is performed before runtime, it is called as a static binding, and the binding which is performed during the runtime, it is called as the dynamic binding. Okay, so let's see that. Now there is a concept early binding also. So this concept is associated with the greater efficiency. Early binding. Early binding, that means before runtime, the binding perform. Association between names and its value will be performed before the execution. Then there is a later binding also. So these times are associated with the greater flexibility. So if we use the later binding, it provides us the greater flexibility. So basically compiled languages use the early binding times, and the interpreted language use the later binding times. Okay. So today we will talk about the binding of identifiers to the variables they name. Now next point is the scope rules and how to control the bindings. So fundamental to all programming languages is the ability to name the data. Okay. So before referring data, we give particular name to that. We give the some identifier to that. Okay. Instead of address, we access that variable with help of the name. Now, in some cases, all data don't have a name. For example, dynamic storage. Okay, so when we use the dynamic storage in the C, it don't have a particular name. Okay, or a Pascal, it is referenced by the pointers, and it is not, it do not use the names. Okay. Now next point is lifetime and storage management. Lifetime of an object and how it is stored onto the memory or in a memory. Okay. So basically there are different key events when a particular variable, when a particular object is created. Okay. So basically first step is the creation of objects. So first step, we create the object. Here we create the variable. Okay. After that, we assign a value to that variable, and that is nothing but the creation of the bindings. Okay, so variable name, it is related with, or it is binded with the address. Again, it is binded with the value also. Now, references to the variables. Here, different references to the variables are used. Then, next, deactivation of the bindings means what? Deactivation means previous bindings will be deactivated and new bindings will be created. Okay, and that is nothing but the reactivation of the binding. After that, there is a destruction of the binding. Destruction means what? Binding will be destroyed, and after that, destruction of the object. Object will be destroyed. Okay, so these are the key events when we create a particular object and when we delete the particular object. In between that, all these events will be occurred. Now, the period of a time from creation to destruction is called the lifetime of a binding. Okay, so when binding is created, the lifetime of the binding will start, and when the binding is destroyed, it is the end of that binding. Okay, so when a particular object outlives binding, it is called as a garbage. Okay, so if object outlives binding, it's garbage. And if binding outlives, means when binding ends, object, it's a dangling reference. Okay, so when binding is not a valid at that time, there is a dangling reference problem. So now first concept is what is the scope? So scope is what? It is the textual region of a program where the particular binding is active, where the particular variable is alive, where the particular variable is accessible. So it is called as its scope. Okay, so what is the scope of a binding? So space or a textual region where that binding is alive, it is called as the scope of that binding. Now next point is the storage allocation mechanism. So basically objects are stored with help of these three mechanisms. First one is the static allocation, next one is stack allocation, and third one is heap allocation. Okay, so according to according to need or according to the program, these three mechanisms can be used. So first is the static allocation. So static allocation, basically it is used for the codes. It is used for the global variables. Okay, then it is used for the static variables and the local variables also. Then this static allocation, it is also used for the explicit constants. So that constant may include the string, set, etc. And the scalars that may be stored in the instructions also. Okay. So static allocation, it is used for the program, that means code, global variable, static variable, local variable, and constants. Okay. Now, there is a central stack. So there is a central stack also. Central stack means what? Stack is a data structure which uses the last in first out principle. Okay, that means LIFO principle. So here stack is used to store the parameters, local variables, and the temporary data. Why we use the stack? As we know that when we use the programs, there are functions, there are recursive functions also. So for that purpose, we use the stack. Okay, and it is used to allocate the space for the recursive routines, and it is used to reuse the space. Okay, so we use the stack for recursive routines and the reuse for the space. Now, when a particular function is called or particular routine is called, what happens? One stack frame is created and that is inserted into the stack. Okay, so stack frame, for each and every function, there is a stack frame. And what that stack frame contains? It contains the arguments and returns. It contains the local variables, temporaries, and bookkeeping information like save register, line number of static links, okay, etc. So it contains all the information related to that function. Okay. Now, local variables and arguments are assigned fixed offsets from the stack pointer or frame pointer at compile time. So, at a compile time, local variables that are assigned with the fixed offset. Okay. So, let us see the diagram. So, this is the stack which contains the stack frame for the different subroutines. At the right side, there is a program. So, there is a procedure C which contains the procedure D and E. Okay, so here subroutines when it is called, so particular here B called itself again. So here procedure B. So procedure B called itself again. So if then B else C, then procedure calls the A, and in a main program there is a call for A. Okay, at the right side there is a program. Okay, so every program starts its execution from the main program. So first of all, A procedure will be called. So the stack frame for the subroutine A will be inserted into the stack. So subroutine A. So first stack frame is for subroutine A, that will be inserted into the stack. After A, in a procedure A, there is a call for the B. So the stack frame for B is inserted into the stack. Okay. Then in a procedure B, there is a call for the B or C. So consider that again next call is for the B. So stack frame for the B is inserted, and again there is a call for the C. Okay, so stack frame for the C is inserted into the stack. In a procedure C, there is a call for the D. So subroutine stack frame for the subroutine D will be inserted into the stack. Now, this subroutine or this stack frame contain what it contains? It contains the return address, then bookkeeping information, local variables, temporary data, and argument to call the routines. Okay, so in this way, the information of a function or a subroutine will be stored into the stack. So maintenance of the stack, it is the responsibility of the calling sequences and subroutine in a prologue and epilogue. Okay, so in prologue and epilogue here, the responsibility of maintenance of the stack will be handled by that. So the space is saved by putting as much in the prologue and epilogue as possible. So time may be saved by putting stuff in the caller instead, or combining what's known in both places. Okay. Now next type of storage management is the heap. Now this heap is used for the dynamic allocation. Dynamic allocation means what? At the runtime. Okay. So particular at a runtime, if your object requires the memory, so that will be stored into the heap. Okay. Now heap contains the different blocks. Some blocks are used and some blocks are free. In this diagram, the shaded blocks are in use and the clear blocks are free. Then crosshatch space at the end of in use blocks represents the internal fragmentation. That means if a particular block is of 100 MB size and only 20 MB is used, then 18 MB size will be the uh, internal fragmentation. It will be none of use. Okay. So discontinuous free blocks indicates the external fragmentation. Okay. Now here the discontinuous free blocks, that means this one. Okay. So these all are the external fragmentation. Okay. So while there is a more than enough total free space remaining to satisfy an allocation request of the illustrated size, no single remaining block is large enough. That means if allocation request is this, but we can't allocate this because there is no single free block of that size. Okay. So in a heap, there is internal fragmentation and external fragmentation will be occur. Okay. So this is the heap and stack. So you can look that here stack the function stack frame for function f1, stack frame for function f2, stack frame from function 3 and function 4 is here. Okay, and here it is the heap which contains the allocated and free block. Okay, and this is the total diagram which contain the stack and heap also. Okay. Thank you.